Lecture 20, functions. There's this great YouTube video. I forget. I don't know that I'm gonna be able to find it again. There's a professor who just starts the lecture by yelling the word functions. Functions rule the world. He's like very, very excited. So somehow Simplicio, I was like, functions. And Socrates says, don't shout, I'm standing right here. Sorry, I got a little excited. So let's talk about functions. Let's talk about calculus. So what do we do in calculus? What's the first thing that you study in calculus? Limits, right? Like derivatives and stuff, right? The first thing you study in calculus is a derivative. Okay, what does it mean to compute the derivative? So what's a derivative? I have some function. It looks like this. Whatever, I have some point. Let's say x equals c. It's right here. So this is c. This is f of c. And I want to compute the derivative here. And so what do? You wiggle it a little bit. Yeah, you go over here to c plus h. This distance is h. H is, well, h could be positive. It could be negative, depending on what kind of derivative you're taking. So this point, this height is what, this is the height of f of c. This height is f of c plus h. For some reason, it's whatever, negative slope here. Then what do? You take the slope, exactly. You take the slope of the secant line. There's a secant line that passes through these 2 points. The secant line is has slope f of c plus h minus f of c. That's the rise over the run, c plus h minus c, also known as h. And then you take the limit as h goes to 0. Of course, not h can't be equal to 0 because then you'd have 0 over 0. So you just take the limit as h goes to 0 of this thing, and that will be, this is how you define the derivative of f at c, right? The secant line turns into the tangent line. The average slope over a shorter and shorter interval turns into the instantaneous slope. Great. So we have to know, okay, so it's the slope of the tangent line. Yeah, what's the expression? It's f of x plus h minus f of x over h. Okay, what word there is problematic? Limit. Limit. What the heck is a limit? Okay, we don't know what a limit is. You can't just stick in h equals 0. So what's a limit? Great. We need to figure out what it means for what this thing means. Now that we're serious about it. Okay. Fine. So remember the engineer and the machinist. Maybe you guys are, how many people already know what I'm about to say for what the definition of limit is? Very good. I'm very, very glad to see that some of you may have seen it, but the vast majority of you have not. Okay. So let's think about the definition. I think we'll call it like fun lim at. So fun limit at is like seqlim. Seqlim is a sequence, has a limit. Now we have a function that has a limit, and I also have to specify where. So this will take a function, f, the limiting value, let's say L, and then where you want to take the limit, let's call that C. And let's try to figure out, so this will be a prop, true-false statement. How can we guarantee that, well, this is a derivative. Forget about derivatives. Before we can talk about derivatives, we need to talk about just limits in general. So if I have some function, here's the graph of a function. Every function looks the same. I don't know why. It's always what is this? It's not even an S. It's like a sideways. I don't know what this is. Every function is a cubic with 3 roots or whatever. I guess I put a double root here. What? Okay. This is a function as far as I'm concerned. How can I tell? And I don't care about its value at this point, right? Here's the point C, and here's the hypothetical limit L. So how can I tell if a function actually converges to L at C? If the limit in a neighborhood of C is L. Other than those who already know. So how did we come up with the definition of limit for a sequence? We had the engineer and the machinist. And the engineer specified a tolerance for the output. And the machinist said, this is the price it will cost you. Okay. So again, the engineer might say, I need the output to be within L plus epsilon and L minus epsilon. Can you guarantee by getting close enough to C, can you guarantee that I'll be within epsilon of L? as long as, as long as what? The machinist has to say, I'll guarantee it if the input you give me, if the value of X you give me is sufficiently close to C. Okay, so it's the same conversation. In the case of sequences, the cost was how far out in the sequence you go. Here, it's how close to C you start with. So the machinist is expecting three things. He's expecting a function, the value of L. He's expecting the epsilon, the tolerance, and an input value of X so close to C, within some range of C, so close that the machinist will be able to guarantee that whatever value he gives back lands in this window. So we can start this with, for all epsilon, that's the tolerance, there exists a what? A delta is the common term. Yeah, delta positive. So we'll get a delta window around C. This will be C plus delta, and this will be C minus delta, such that as long as you go up far enough in the sequence, for all n greater than or equal to capital N. Jeffrey.
For all x such that absolute value of x minus c is less than delta, then you have f of x minus L is less than. So
yes, not f of c, because f of c could be something else. We're not saying we have nothing to do with the value at the, a limit has nothing to do with the value at the point C. It's just near the point C. And so we have this limiting value L, and we want to know that that's within epsilon. Okay, you give me an X that's within delta of C. I have to give you the delta, and then I'll guarantee that the function value will be within epsilon of the limit that you want. Okay, does that make sense as a definition? There's one thing wrong with this definition. Okay, so Simplicio says the machinist is going to talk about running the process for at least 10 steps. So we make sure your input X is within a distance delta of the target point C. And so the engineer says, I want the function to be within epsilon. The machinist says, no problem, just make sure the X you give me is within delta of C, and I'll guarantee you the output tolerance. And if you can do that for any epsilon, if for any epsilon there exists a delta, so that if you give me an X that's within delta of C, the F that I give you back will be within epsilon of L. Okay, it's exactly the same principle as we've already seen. There's one problem with this statement. And what is it? Joe. Exactly right. This is actually the definition of continuity, because it includes the point X equals C. So what we have to add is one more thing. We have to exclude the possibility that X equals C. We do not want to evaluate this. This would not be, if we had this picture and the value at C was some random point way off the chart, this would not give you, we would not be able to say that this function has a limit of L. And that's a big problem when we go to derivatives where we have 0 over 0. We do not want to allow h equals 0. So it's essential that our definition of limit exclude the possibility that x equals c. Okay. Other than that, that's the only thing that's slightly different from how sequences work, sequential limits versus function limits. Okay. So what's wrong is, remember what continuity is. The first thing you learned in calculus was limits. The second thing you learned was continuity. So recall, just in natural language, f is continuous at x equals c. If what are the two conditions?
If
I went.
the limit actually exists.
Exactly. Exists. Okay, if there is a limit, if there exists an L so that there is a limit, and exists, and let's say is equal to L, and the value of the function at C is L itself. Okay, so this doesn't happen. This gets dropped back to where it's supposed to be. That you can capture with exactly this same definition, just without it insisting that x is equal to c, because it includes the case that x is equal to c. Okay, so this captures continuity, whereas this captures limit. Does that make sense? Right. And so here's the real definition. For all epsilon, there exists a delta, so that for all x not equal to c, if x minus c is less than delta, then f of x minus L is less than epsilon. Pretty easy. Okay, and this is called the punctured neighborhood of C. If X is in a punctured neighborhood of C, it's in a window of C, but you're not allowed to take C itself. So you're like, you pop 1 point out of it. And then why do you want to do that? It's because when you were doing calculus and you were finding limits of things like x squared minus 1 over x minus 1, you would say, well, I can factor the numerator and cancel as long as x isn't equal to 1. And I can't do that cancellation if x is equal to 1. Okay, so that's exactly why we want to record this. And you'll see very explicitly, maybe you thought that was stupid, right? X squared minus 1 over x minus 1. Come on, it's x plus 1. Everybody knows that you can cancel the x minus 1 on top and bottom. No, lean won't let you cancel them. It's not true. 0 over 0 in lean is defined to be 0. It's just some junk value. The point is, this completely captures everything that's going on. All right, let's do it. Does that make sense? The definition makes sense? How we came up with it, why it's the right definition? Let's see if it does what we think it should do in practice.
I understand why this definition works, but I have a question of whether this alternative definition is also equally valid.
This one here?
No, like what I'm going to propose.
Oh, propose a definition. Beautiful. So fun lim at prime.
Yeah.
You give me a function, you give me an L, and you give me a C. What is it?
For all x.
For all x.
Yeah. Series lim.
You mean sequence lim?
Yeah, I mean sequence lim. Sequence lim.
Pause your comment for 25 minutes. You're going to say, why don't I just take some sequences that converge to the point C and never hit the value C? Can't I use that as a substitute for limits? Pause that for 25 minutes. You're right on track. Okay, so not yet. Oh, come on. Anyway. Come on. The eraser is a little too smart. It erases once and then switches back to a pen. Okay. Yes. Very good. We're going to come to that. All right. Round one, let's prove. So we have this new definition, fun lim at. A function has a limit at a point, and the name tells you in what order they come. Give me the function first, then give me the limit, then give me the point C where that happens. And what we're going to do is exactly what we said, x squared minus 1 over x minus 1. I want to know, does there exist an L so that fun lim at x squared minus 1 over x minus 1, L at 1. Okay, so theorem, there exists an L. There are no assumptions. We have no hypotheses, no assumptions. We just want to say there exists an L so that fun lim at x squared minus 1 over x minus 1 has limit L at x equals 1. Okay? How do you prove this? Step 1. Sean. Excellent. Does everyone agree that 2 is the limit? So step 1, use 2. Okay, what is this function? We all know that this function is x plus 1. X plus 1 looks like this. Here's a 45-degree angle that goes through 1. Okay, this is y equals this thing. That's the graph. At x equals 1, this is x equals 1. Actually, it has a hole, and there the value is literally 0, but the limit is still 2. Okay, so use L equals 2. Beautiful. Now we have to show that fun lim at this thing is 2 at 1. Roger.
Why is the value below 0?
Because when x is equal to 1, the numerator is 0 and the denominator is 0, and 0 over 0 is 0. Has a junk value. Damien. Intro epsilon. It's the same. Yeah, intro epsilon, h epsilon. Okay, so we have an epsilon, a real number, and we have h epsilon that epsilon is positive. What is the goal state right now? Goal, there exists a delta greater than 0 such that for all x not equal to, and c is 1, for all x not equal to 1, excellent. Okay, so our window, I don't know what epsilon is, but our window is we have to be within epsilon of 2. This is 2 plus epsilon. This is 2 minus epsilon. How much within 1 must I be to guarantee? Exactly. Because it's just linear, I can use the same epsilon. The same epsilon, it's linear and has a 45-degree angle. It's line y equals x. I mean, as far as the slope is concerned. So I don't have to worry about what these points are. This can be 1 plus epsilon, and this can be 1 minus epsilon. And if you're in this window, then the values will all be within that window. So if I have to show there exists a delta, which delta do I give? Epsilon. So that's use epsilon. Okay, so now I have two goals. Delta is positive and yada yada. Yeah, you can split ands and apply, or you can use, so this is like a slightly fancier use, you can use epsilon comma h epsilon, because we already know that delta is positive. Or by bound would be fine if this was epsilon over 2 or something. Okay, so it's use epsilon comma, and then some stupid proof that the thing that you're saying is positive. Now our goal is for all x not equal to 1, if x is minus 1 is less than delta, then f of x is less than epsilon. Intro x, yeah, give me the x. Yeah, give me the fact that it's not equal to 1. You want to call that xne or something? X not equal to? And then what? It's still intro because it's if there's nothing to prove unless x minus 1 is less than delta. So let's just call that hx. Okay, so now we have three things. We have a new real number called x. We have a hypothesis xne, which is that x is not equal to 1. And then we have another hypothesis called hx, which is that x minus 1 is less than epsilon, because we set delta equal to epsilon. So it's going to say epsilon. That's the trick. I wanted you to say delta. Thank you. That's right. But we've set delta equal to epsilon. And our goal now is to show yeah, and f of x is this complicated thing. So it's x squared minus 1 over x minus 1 minus 2 is less than epsilon, knowing that x minus 1 is less than epsilon.
Like factor and like field sim if you know that it's not 1.
That's exactly what we need to do. That is exactly what we need to do. So well, so let's try this. You're right. I'm leaving a little space here because it will fail. Let's try rewrite. Show x squared minus 1 over x minus 1 is equal to x plus 1. By what? Field simp. Let's cross multiply. Field simp. And then we have x plus 1 times x minus 1 needs to be x squared minus 1. Ring NF. Okay, this won't work. And the reason it won't work is it doesn't know that x minus 1 is not 0. So let's do a little have first. Have some fact that x minus 1 is not equal to 0. Linearith, maybe we'll do it. Bound will do this. bound will do this. There should be, I'm trying to get them to help me make a tactic just called obvious. The packages, linearith, bound, simp, grind, just throw everything. Like I should not have to think about which is it norm, num, or bound, which tactic is going to make progress on it. Okay, so this is where it's essential that in the limit definition, we had the hypothesis that x is not equal to 1. Without that hypothesis, it's simply not true, let alone we can't prove it. Okay, we would not be able to prove this without this hypothesis. Once we know that x minus 1 is not equal to 0, field sim will cross multiply, and then ring will multiply everything out. And so now the goal becomes, the new goal at this point says, once I change x squared minus 1 over x plus 1 to x minus 1 to x plus 1. Sure. Now what? Yeah. Yeah, let's do it properly. We will rewrite show x plus 1 minus 2 is equal to x minus 1, and that's by ring. And now what is the goal? Which is apply hx. Cool? You just proved your first limit, Damien.
Can you use epsilon here?
Yes.
And that was because it's linear and also 45 here.
Yes.
Is that because both, like, if it were not, the slope just being 1, if it were like the slope of 2?
Save your question by 3 minutes. The next thing is going to be nonlinear because that's not always this easy. Exactly. I gave you the easy one to start. Right? We're going to build this up. That's the easy one. The easy one is you don't have to think about what you have to do. Then we're going to have to think about what to do. Okay. But so far, everyone's happy? All right, let's put it in. So we have to, this is nice because it fits right here. So which value of L? Use 2. Okay, we have to prove fun lim. Intro, epsilon, h epsilon. All right, what value of delta? Epsilon. Use epsilon, comma, h epsilon. That clears both conditions. If you didn't put the comma h epsilon, you would have 2 goals, that epsilon's positive and this. You could split them if you really wanted to. And then for the first one, just apply h epsilon. Okay, or you can do them all at once. All right, for all x, as long as x is not equal to 1, and as long as x minus 1 is less than epsilon, something. Intro, x is not equal to, and hx. Now our thing is, oh, this is ugly. Okay, so let's just do a little change. You see, it's the function that maps x to x squared minus 1 over x minus 1, evaluated at x. Let's just do a little change. I don't need the function. When you evaluate this function at x, you get this thing. Oh, come on. One parenthesis missing. Okay, it took it. Okay, now let's do this intermediate step in order to help field simp. So have the fact that x minus 1 is not equal to 0. Great, it knows that x minus 1 is not equal to 0. Let's rewrite show that if you take x squared minus 1 divided by x minus 1, you'll get the same thing as x plus 1, and that's by field simp and then ring. Cross multiply and do a ring operation. I think it did it. We'll find out. Maybe we'll get to the end and there'll be a problem. So it did it. The new goal is x plus 1 minus 2. Rewrite show x plus 1 minus 2 is equal to x minus 1 by ring. That's easy. And then we have exactly hx. Question, Sean?
Not directly related to this, but say you were doing it at like a different point that wasn't 1,
Mm-hmm.
and then near like delta neighborhood, you have 1 in it, and like, but like your explicit condition is not x not equal to 1, it'd be like x not equal to 2.
Wait 3 minutes. Yep, that's the next. Guys, this is, I know little about pedagogy, but I know something about pedagogy. Yeah, we're going to build up the levels of difficulty exactly incrementally. Yeah, yeah. And now the last step, apply hx. Yeah. And it did it. Okay, there was no problem with the bound or the field simp or anything else. Let's do a slightly harder problem. Okay, what's the next one? Oh, right, I wanted to go back and forth between the continuity definition versus the limit definition. So the continuity definition is literally the same thing with one less step. I don't say x is not equal to c. Okay, let's prove that what? Okay, so this is like limit, but we don't have to, there's no division. So it's a harder function, but an easier thing to prove about this harder function. New theorem. So are we happy with this? The definition is the same. It's function continuous at. There's no limit to specify, it's just continuity. The limit is f of c at. And the definition is exactly what it says here. Where does it say it? Yeah, right here. For all epsilon, there exists a delta, so that for all x, not excluding c, if x minus c is less than delta, then f of x minus f minus not L, but minus f of c is less than epsilon. Okay, everybody clear on that distinction? All right. Great. So our theorem is the function x squared minus 1 is continuous at x equals 2. All right. Now we have to think. Well, the first couple of things we can do mechanically. What should we do first? Yeah, let epsilon be given. Exactly right. Intro epsilon h epsilon. And now what value of delta should we use? Now you have to, I don't know how you like to do it. I have to draw a picture. Okay, x squared minus 1 is a parabola. Here's x squared minus 1. Let's see, when x is equal to, the roots are at minus 1 and plus 1. When x is equal to 2, what's the value over here? 4 minus 1 is 3. Very good. And now I've been given an epsilon. Now I have no control on this epsilon other than it's positive. So first of all, it might be 1,000, which, you know, you don't want to do arithmetic like that. So maybe we want to first assume that epsilon is less than 1, or if epsilon is bigger than 1, replace it by 1. So let's think of epsilon as being small for a sec, like reasonably small. So here's 3 minus epsilon, and over here is 3 plus epsilon. And I want to know what this value is, and I want to know what that value is, and I want to, you know, take the smaller of the two or something. I want to be able to, how am I going to solve this problem? I have to return an interval, and an interval centered around 2. Is this a good quiz, or is this still too hard? Let's do one together, and then I'll give you one to do by yourself. Like, Akil. You can. You can. You will not get, you know, it will not be nice to work with the function that you get as a result of, you know, adding 1 and taking square roots. To prove that the interval you get, yeah, you could just take the minimum of the inverse function at these 2 points. It will be very unwieldy to work with. You want to be slightly smarter than that. Wait. Sean.
Like when you simplify x squared minus 1 minus
Yes. Let's think about, so here's some scratch work. X squared minus 1 minus 3, because the limit's supposed to be 3. What is this? Yes, it's x squared minus 4, which is x plus 2 times x minus 2. Ah! X minus 2 is there. Right? It sort of has to be there if the function is going to be continuous. Then this difference is going to have a root at x equals c. That's not an accident that the x minus 2 popped up. It's going to be there. The question is, what are we going to do about this other term? So how bad can x plus 2 get? Well, yeah, it depends on how large you allow epsilon to be, but you're absolutely right. If we let epsilon be at most 1, then this will be at most 4, and the square or whatever, this will be like the square root of 5. I think we can make this x plus 2. If x is between, let's say, bless you, let's say x is between 1 and 3 or something, then x plus 2 will be at most 5. So note, if X is between 1 and 3, so that's a window of size 1 around 2, then X plus 2 is at most 5. In fact, in absolute value, it's at most 5. So if this part's going to be 5 and this part's going to be delta, then we have a pretty good shot of doing something, right? This difference, so if I put absolute values here, I'll get absolute values here. We're assuming that this part's at most 5. We're assuming that this part's actually strictly less than delta. And I want this to be at most epsilon. That's a nice, clean way to figure this stuff out. It's going to take a little bit of practice. Okay? You look at the difference between your function and the value that the function is supposed to take. If it's going to be continuous, it has to have x minus c as a factor. Like, let's look at it in general. If I look at f of x minus L, that has to be x minus c times something. You just make this something small by restricting the range of x. And if you can do that, then you know what value to take delta in terms of epsilon. If this thing is at most m, then you'll have that this is at most delta and this is at most m, and you want that to be epsilon. That's a general principle. Does that make sense? Thank you. Sure. How do I get the thing in the note?
Yeah.
If x is between 1 and 3, then x plus 2, I'm just adding 2 to both sides, is between 3 and 5. In particular, in absolute values, it's at most 5. Because I'll take absolute values here, which means I get absolute values here. X minus 2 is going to be less than delta by assumption. I just don't know what delta is yet. This I can make at most 5. And so I can make this at most 5 delta, but I want it to be at most epsilon. So I just set delta equal to epsilon over 5. Or 1, whichever is smaller. To make sure that if epsilon is huge, epsilon over 5 doesn't help me. Does that make sense? It makes the analysis more annoying. I'm doing f of x minus f of c is less than epsilon. That's what I want to prove. That's what I have to prove. Under the assumption that x minus c is at most delta. But I have to tell you what delta is before I can do it. And delta has to be a function of epsilon. And what function of epsilon should it be? I claim it's epsilon over 5, unless somebody gave you epsilon equals 1,000 for some stupid reason. Just restrict this to this window. I'll show you how to do that in a second. I haven't told you how to do it.
It's working back.
That's exactly what it is. That's exactly what you have to do. You work backwards to figure out what the answer is, and then you work forwards. This isn't the proof. This is the scratch book.
Yeah, but it just feels like by construction that implication is true.
Yeah, but we have to prove it.
So are you claiming that like f of x minus L will always have a factor of x minus?
If f is actually going to L, then at C, then this, when x is equal to C, should be 0, if you actually have continuity. And if this is a nice function, what it means for this difference to be 0 is that you can pull out x minus C. If it's like a polynomial or a rational function. Okay, you should be able to find some decomposition like this. It's not always going to work. Like sometimes you'll need to take delta to be epsilon squared, or whatever. There's a wide variety of things that happen, but this is a pattern that you should be on the lookout for. I need to give you lots of exercises to condition you to look for this kind of thing. Okay, so let's let delta be what? The minimum of epsilon over 5 or 1. Minimum is a function that takes two things and returns, the smaller of the two. It's like an if then else, but it's all packaged in. Okay, that's delta. We should, of course, use, so what should we do next? What's the goal at this point? Sorry, we haven't done the use delta yet. The goal is there exists a delta and delta is positive. So if we use delta, I don't know if bound will do it. We can try by bound. Maybe it will, maybe it won't. So that'll prove the positivity of delta. And now we have to show for all x. So now the goal at this point, the goal says for all x, if x minus c is less than delta, then we have to show that f of x minus f of c is less than epsilon. So what do we want to intro? X and just hx. There is no x not equal to. That's the difference between continuity and limit. Okay, so we intro x, we get this. We intro hx, we get that. This is hx. And now we have to prove this. Okay, in our case, f of x is x squared minus 1. So our new goal will be the absolute value of x squared minus 1 minus what? Yes, exactly. Where c is 2. Yeah, minus 2 squared minus 1 is less than epsilon. But what is this? This is x squared minus 4. So let's rewrite, show this whole thing, x squared minus 1 minus 2 squared minus 1 is equal to x plus 2 times x minus 2 by ring normal form. Okay, so now this is turned into x plus 2 times x minus 2. Now what? Absmol, right? So let's rewrite, show the absolute value of x plus 2 times x minus 2 is equal to the absolute value of x plus 2 times the absolute value of x minus 2. I think bound will also do this, I recently discovered. Yes, but it's apply absmol or something. But bound will do it for us, okay? So now our goal is that this thing is less than epsilon. Now we have to prove what? Sean?
That x plus 2 is bounded by.
Exactly. Let's have the fact f that x plus 2 is bounded by 5. Okay, how are we going to do that? Sean? Yes. Let's.
I'm sorry, you would say like absolute value of x plus 2 is equal to the absolute value of x minus 2 plus 4, which would be less than.
Oh, okay. I like that. I like that. You can do it that way. I was just going to do something much dumber, which is to break this up using abs LE or something. But I like your way better. Let's do your way. So your way says, if I understand correctly, x minus 2. This is x minus 2 plus 4. And this is at most x minus 2 plus 4. And x minus 2 we know is at most 1. Is less than 1. I like it. So let's build that up. So we have, first of all, let's record that. I think it'll be useful to record that let's call this F1. X minus 2 is less than or equal to 1. I think bound should be able to, we know that x minus 2 is less than the minimum of 1 and epsilon over 5. So that's where that 1 comes in handy. And it should be able to do that by bound. And then have F2 is that, I guess we could say, well, this will be useful also in the other one. Although, let's write down that also that x minus 2 is less than or equal to epsilon over 5, also by bound. because that's what we'll use the second time around. So we're sort of we're recording the two minima as two different facts. That's what the minimum is. The minimum is give me both of these conditions. Okay, great. And then have F3 is that, yeah, let's just go straight to it. X plus 2 is less than or equal to 5. This is going to be by, first we can rewrite show x plus 2 is equal to x minus 2 plus 4. This is by ring. Everybody with me? Then we can have F3 prime or something, that absolute value of x minus 2 plus 4 is less than or equal to x minus 2 plus absolute value of 4. This is by apply abs-add. Triangle inequality. Okay, and then I think just linearith. I hope linearith will do it. Maybe, does it know that the absolute value of, yeah, maybe linearith should do this. Linearith with just with F3 prime. Okay, we'll see if that works or not. All right, that gives us that x plus 2 is less than or equal to 5. Should we do this not in the game, but in the, do you guys prefer to do it in VS Code? Let's see. Thank you very much. I absolutely need F1 as well. Yep. So this decomposition together with F1 is what tells me that x plus 2 is less than or equal to 5. Beautiful. Okay, and then I guess we have to do something like have F4. F4 is that x plus 2 times x minus 2 is less than or equal to 5 times x minus 2. Maybe we have to do it one at a time. Maybe bound won't let me multiply the two together. Maybe it will. Should we be bold? Let's be bold and say this is at most epsilon over 5. And that's by bound. Maybe it'll get it, maybe not. Maybe we have to break it. So far, so good. And then we're done. And then maybe linearith F4 should close it out. Okay. Should we try it in the game? Okay, let's try it in the game. It's a little maybe even in the game we can go to how do I get to the editor mode? Should we do it in editor mode? Because I'm not sure which of these tactics will or won't work, and we won't be able to tell otherwise. All right, any questions on this before we do it in the game? Does it make sense what we've done? Does it make sense how we figured out what the delta needed to be and what the strategy is for that kind of thing? All right, we want to show that x squared minus 1 is continuous at 2. Intro, epsilon h epsilon. Great, there exists a delta. Let delta be, should I just use or let? Let's do a let. Minimum of 1 and epsilon over 5. Okay, so we have our delta. Use delta, and let's see if by bound we'll do it. You did it. No red stuff. Okay. Intro x hx. So we're here. Great. Now it's this ugly thing, Daniel. So because now it's not just that there exists a delta, but that there exists a delta and a proof that delta is positive.
I thought when do multiple stuff.
With use, you need a comma. Again, if you don't want to do it this way, you can just use delta. Then you'll have two things to prove. Then you split the ands. And now you're just staring at why is delta positive, and then I'll do bound. And that closes it out. Yeah. Okay. For all x, so intro x hx. This is too ugly for me. I have to change it. I don't know what it says. So change. The function that sends x squared minus 1 at x, evaluates it at x, versus the function that evaluates it at 2. That difference is epsilon. That looks much nicer. Okay, and now I want to rewrite rewrite, show this thing is equal to, what is it going to be? This is 3 and this is x4, but I want to say x plus 2 times x minus 2, and this is by ring. No problems. Beautiful. Okay, let's rewrite, show this thing in absolute value is equal to the same thing, but now with absolute values here and here by, I think bound will do it. Let's see. Oh, it doesn't like that I didn't put a space there. A little too picky. Okay, so far so good. So now we're at, where are we? We did this and bound worked. Let's have F1. Have F1 is that x minus 2 is less than or equal to 1. This is by bound. Bound should, no. No, bound won't see that x minus 2 is less than or equal to 1, given that the minimum. Okay, let's try norm num. Which one? No. Let's try. Which one did I get to work? I got one of them to work. Does it know that 1 is a real number? It does know that 1 is a real number. It knows that 1 is a real number here. It's not a casting thing. Are you sure, bound? Come on. All right, let me cheat and see what I used. This is level 2, right? Level 2. When I got this to work, so you see I changed it. What? I see. All right, so what bound did is it proved this. Actually, norm num did it too. Okay, that it can do. It can show that the minimum of 1 and epsilon over 5 is at most 1, but not the other way. Fine. Good. A little bit of experimentation. Let's record the other one before we forget how to do it. That's a little bit of a little bit annoying, but let's call these primes. And now we should be able to prove the one that we want. Have F1 is the fact that where's our work? That x minus 2 in absolute value is less than 1. Less than 1. Now I think bound will do it. Yeah. So it'll do it. It'll do both of these steps, but not together. It'll tell you that the minimum of 1 in this is at most 1. It'll chain this and the other one and give you that, but not in one fell swoop. Sorry. It is, that's life. F2 is that this difference is at most epsilon over 5. Bound will also do that. Okay, now we're up to F3. F3 is the kind of the beef of this argument. Is why did we choose epsilon over 5? It's because x plus 2 is at most 5 in this range. So let's see if we can do this. Have F3 is that x plus 2 is less than or equal to 5 by. Okay, first we're going to rewrite. Can I do it like this? Let's see. Yeah, so now our goal is x plus 2 is less than or equal to 5. Okay, so let's rewrite. Show x plus 2 is equal to x minus 2 plus 4. And I think I have to put parentheses around the x minus 2 so that it does it correctly. This is by ring. Beautiful. You see the goal down here? That changed to that. And now have F3 prime, which says that the absolute value of x minus 2 plus 4 is less than or equal to x minus 2 plus absolute value of 4. And this is by apply abs add. And now we have this fact by abs add. And finally, linearith, which will probably need F3 prime, F1, and F1. Oh, I guess F1 already says what I needed it to. No, really? Oh, because of the 4. Oh my God. Rewrite, show absolute value of 4 as a real number, God, is equal to 4 by norm num. Okay, so now that, that's at F3 prime. Okay. We have to make that absolute value of 4 into a 4, then linearith works. Okay. All right, so we closed out that F3. And this is where switching to editor mode is really helpful. Is any questions on how we did that? Everybody see how we did it in Lean and also what it means mathematically. And finally, we're done. Have F4 is that the absolute, well, we'll see whether we're done or not, times x minus 2 is less than or equal to 5 times epsilon over 5 by bound, please. It did it. Sometimes it makes me, no, it didn't do it. It pretended to do it when I wasn't looking. All right, let's do it 2 steps or 1 step at a time. X minus 2. This I think it can do. Beautiful. And have F5, which is 5 times x minus 2 is less than or equal to 5 times epsilon over 5. That it can also do. And now, Linnerith, F4 and F5. Failed. This product. Thank you. Thank you, thank you, thank you. That's, I've done that before. You would think I should learn that lesson now. The not strict is voted. Okay. Does everyone understand how to prove continuity and the difference between continuity and limit? There's only one difference, which is the not equal. Sean Mending.
So F1 and F2 should also be strict inequality.
F1 and F2 are not strict inequalities because they are about the minimum, and the minimum could be 1.
But if the minimum of, like, since it's less than or equal, or it's less
These could be, yeah, you're right. Yeah, because this is strictly less than the minimum. Yeah, you're absolutely right. It apparently didn't hurt, but let's add the strict inequalities and make sure that bound picked it up. Yes. Thank you. Okay, any questions on continuity? I was going to go to Daniel and then John.
So, okay, I'm wondering why you define continuity explicitly like this. Because I remember when I was thinking calculus and defining it as just function equals limit at a function.
Yes.
I see how they're equivalent, and that's probably not difficult to prove. But like, why is it useful to have this separate?
It's a much nicer thing to work with to do this just without the not equal C than to prove the limit and then also prove this one extra thing. So maybe I'll give you a homework that says if these two things are satisfied, then that, and if that, then these two things are satisfied. Just so that you can convince yourself that yes, they're equivalent. But that this definition is just much nicer to work with. Yeah, the choice of definitions is really important when you're doing things formally. This on paper is the same thing, and we would all agree, but then do it. Use this, and it's just a hassle. It's more work. John.
Can you scroll down on scratch a little bit? Yeah.
Higher, lower?
I'm looking for a little lower. Yeah, right there. So we said if X is between 1 and 3,
Yes.
right? And did we kind of like do a little case analysis there or something? Like we restricted it for epsilon big and epsilon small in essence. Like,
That's it. That's exactly what the minimum does.
okay.
Yeah.
Okay.
So the X being restricted to 1 and 3 is that we're taking delta to be the smaller of 1 and epsilon over 5. So if the engineer comes back and says, you know, I want 3, but give or take 5. You're like, dude, that's too wide a range. Like my output's going to be well within that. You're not giving me anything to work with. So I'm just going to give you 1 back as the range. Or if you give me a very precise epsilon, now forget about the 1, go to your tolerance over 5. That's exactly where that switch happens. Okay.
What's like the under the hood definition of?
You don't want to know.
Oh,
Well, okay. You can call it if the first thing is greater than the second, then it's the
okay.
first, else the second. That's one way you can think of it.
But when you first introduced min, I kind of assumed that we have to do like a by cases kind of thing.
So what you can do instead is the minimum of two things is less than or equal to either of them can be proved by bound. So do not break it by cases.
If we didn't have bound, the,
You would say min LE left and min LE right, and you don't want to. I don't want to teach you more things than bound handles it. Great. Unfortunately, it doesn't handle it one step later, so I have to break it up into two steps. But otherwise, it works. Okay, we're happy with this. Let's switch back to typewriter mode so that we can see that everything worked out nicely and go to the next level. Next, sum of continuous functions. This might be a good quiz. Okay, f and g are both continuous at C. Why is f plus g continuous at C? I think you could just do this directly. Okay, here's the theorem. The theorem is called, does it have a name? Thought I gave it a name. Yeah, here it is. Function continuous at add. So the name of this theorem is, continuous function at, this is a bad name. It should be called function continuous at add. All right, and what it says is you have two functions, f and g are functions. You have a real number x equals c. You have the assumption hf that the function continuous at f is continuous at c. Hg is that function continuous at gc, and your goal is function continuous at the function that sends x to f of x plus g of x is continuous at c. Okay, take 45 seconds and prove this for yourself.
Using natural language or?
Sure, do it in natural language. And if you need a hint, let me know. The goal?
Yeah.
Fun continuous at. Oh, you want to remember what that means? Oh, what's in the parentheses? It's f of x plus g of x.
Oh, awesome.
Yeah, the function that maps x to f of x plus g of x. You can see it here.
Okay.
Good that you're getting practice writing things, but there should only be two ideas. What are the two ideas?
I was thinking that you gotta specialize the HF and HG to epsilon.
Epsilon over 2, that's one idea. And the other idea? Right? Triangle equality, yeah.
The delta to be the min of the.
Delta's the min. There's two ideas. You use epsilon over 2, and which delta do you take? Well, you get a delta from F, you get a delta from G, take the smaller. And then triangle equality, of course.
Are you only introducing min now because you can't like add?
That's exactly right. The reason I'm introducing min is because there's no way to, adding the deltas is not, does not help. I have to introduce the min. You could also force the deltas to be a post one and then you take their product, but at that point, you're like, just use the min. It's not worth it. Okay, should we do it in natural language? Is everybody ready? Does anybody want more time or can we go? 2 minutes. Let's do it all together. Okay, so let's do it in natural language. How do you start? Let epsilon be given. Then we get by HF, we have delta 1 so that for all x minus c less than delta 1, f of x minus f of c is less than epsilon over 2. By, or similarly, choose delta 2 using HG so that x minus c less than delta 2 implies gx minus gc is less than epsilon over 2. Then use delta equals delta min delta 1 delta 2. Then if x minus c is less than delta, we need to show that absolute value of x plus g minus f of c minus g of c is less than epsilon. So we compute, so f of x plus g of x minus f of c plus g of c is equal to f of x minus f of c plus g of x minus g of c, which is less than or equal to those two things, but with absolute values there, and that's less than epsilon over 2, strictly less at some point. I need a strictly less. Okay. This is what I mean by there's only one idea, or two ideas. One idea is epsilon over 2. That gives us a delta, and the fact that delta is positive. We take the smaller of the two. Of course, we have to prove that the smaller of the two is positive, and then we take x less than either. In the first case, that gives us epsilon over 2. In the second case, gives us epsilon over 2. Let's go straight to a formal proof. Does that make sense? Any questions on this? Is this basically what you guys wrote? We're getting really good at this. Okay. Intro, epsilon, h epsilon. All right. Where am I supposed to get the delta? Choose delta 1 and h delta 1. Well, I need the positivity, delta 1 positive. I'll just make it 1 instead of something fancy. Positive and h delta 1 using HF, where I stick in epsilon over 2. And why is that positive? By bound. Okay, everybody See that that's the right thing to do? I'll copy that. Hopefully that'll work. I'll paste it and do a delta 2. Oops. Delta 2. Delta 2 is positive. H delta 2 using HG. Okay, I got my delta 1. I got my delta 2. Use min delta 1 delta 2. Okay. Split ands. Bound, please. Thank you, bound. All right, bound. You're the man. Intro x, hx. So now I have that x is less than delta 1 and x is less than delta 2. So let's see if it'll work. Specialize h delta 1 to x and by bound. It couldn't do it. Fine. So not specialized yet. Oh, come on. Oh, I have to hit retry. Let's just go to editor mode. Okay, good. Just in case it didn't actually delete it. So I need to know that x minus c is less than delta 1. Have f1 is that x minus c is less than delta 1 by bound. No. Okay. Have f1 prime is that min delta 1 delta 2 is less than or equal to delta 1 by bound. And then it won't do it. It did work. Okay, good. And then let's do the same thing with f2. This is at most delta 2. And f2, that's at most delta 2. Okay, now let's specialize. Specialize h delta 1 to x together with f1. Yes. I got that f of x minus f of c is less than epsilon over 2. Now specialize delta h delta 2 to x and f2. And that gets me g is at most c. Okay. I won't bother to rewrite this nicely. Oh, come on. Out of the way. So let's rewrite. Show this annoying thing is equal to what? Get out of here. F of x minus f of c plus g of x minus g of c using ring. What's the matter? F of x, this minus this, that. Oh, and I have an open parenthesis. Let's try this. Open parenthesis here. That's what it was? Oh, by. Sorry, by. Show. Open parenthesis, close parenthesis. Open parenthesis, close parenthesis, close parenthesis. There we go. Okay. So now we have this. Okay. Have F3, which is this thing is less than, yeah, good. It's less than or equal to this plus that by apply abs add. Okay, good. And that's the most epsilon over 2. That's the most epsilon over 2. Okay, so now it's linearith with F3, H delta 1, H delta 2. Linearith, H delta 1, H delta 2, and F3. Boom. Okay, next. Any questions? Easy? You could do this? Okay, let's go. Blazing right through. Safik, could you ask your question, please?
I'm gonna propose it to also define function limit in terms of sequence limit.
Excellent. That's a great question. I wish I had thought of that. All right. So how could these concepts not be connected? It's mathematics. Mathematics is a beautiful subject. All right. So the forward direction if f has a limit at L at C, then no matter what sequence you take that converges to C, but is never equal to C, then f of xn converges to L. That's the theorem. Okay? So let's do one direction, and then the next level is the other direction. This is one of the most wonderful things in mathematics. So theorem, f goes to L at C if and only if, we're only going to prove one direction, for all sequences xn converging to C and xn never equaling C, f of xn, which is now a sequence, converges to L. Okay, so what's going on is we have a function, we have a point C and a value L, and I don't know what's going on here, but this kind of convergence is continuous convergence. I want to know for all epsilon, does there exist a delta, so that if I get within delta, then the value will be within epsilon. This is a sequential convergence. You give me any sequence of x's that get closer and closer to C. That gives me a sequence of function values, and I want to know that that sequence of function values, whatever they are, as a sequence gets closer and closer to L. Daniel.
Why do you need that X number?
Because I could take the constant sequence, C, which definitely converges to C.
But it's now.
So to be an if and only if.
Oh,
If you give me a sequence and that sequence is the constant sequence of all C's, I will not be able to prove that f of that sequence is always equal to L, because it might be equal to some junk value.
Need that all sequences,
Yes?
like for the other direction.
Well, let's look at this direction. So it says, so we have a function f, we have two real numbers L and C. We assume that f goes to L at C. Then it says, for any sequence, no matter which sequence it is, if I remove this hypothesis, as long as the x's go to C, then the sequence of f of x's goes to L. That might be false, because the function that you give me is all C's. I say, not only do I not want the all C's function, the only functions I'll allow is functions that just never touch C. I mean, this is too strong a condition, but you're right that you could say, you know, eventually it never is equal to C or something. I'm just going to say for all values, it's not equal to C. Does that make sense? Okay, so let's prove this. Let's see if we can prove this in 6 minutes. Should we go straight to the formal proof? So give me the sequence, intro x, so that's a sequence, that's a function, it's x1, x0, x1, x2, and so on. Give me the fact that it's never equal to C, so that's xne, is that none of the values of the sequence are equal to C. Give me the fact that x goes to C, that's hc, hx, let's say. And then I have to prove that the sequence of limits converges. Okay? So the sequence of limits, what is the sequential limit? Do we still remember how sequential limits work? For all epsilon, there exists an n. Okay, so intro epsilon, h epsilon. And now I have to produce an n so that f of x of n is within epsilon of L. How do I do that? How do I make sure that the x's are within epsilon of L? Jeffrey.
Get a delta value for like HF.
Exactly.
Specialize those.
Exactly right. For that epsilon, for that same epsilon, HF says if the xn's are within delta of C, then f of xn's will be within epsilon of L. Okay, so let's do it in several steps just so we can see it all. Specialize HF to epsilon h epsilon, right? Because this says for all epsilon there exists a delta. So there exists some delta, so that for any x values, yada yada. So choose that delta, delta positive, and h delta using HF. Okay, so we have a delta. And then we know that for any value, as long as it's not equal to C, if x minus c is within delta, then f of x minus L will be within epsilon. So far, so good? Now what? Joe?
Specialized HX to delta.
Yes, this says when you go far enough out, x and c will be within whatever you want of each other, including delta. See how nice this is? So I'm going to specialize hx to delta, and the fact that delta is positive. That says there exists an n, so that once you're past that value, xn minus c is less than delta. Sorry? Exactly. Choose n hn using hx. And which value of capital N should I use in the goal? That value. Use n. Now give me a little n, intro n hn. And now I have to prove that f of xn minus L is less than epsilon. So what should I do with h? What should I do? Keep it away. Sure. Exactly. Okay, great. Specialize h capital N to little n and hn. So now we know that xn minus c is less than delta. Other than Sean? John? H delta to xn. So I have to give it an xn. Then I have to prove that xn is not equal to c. Yep, that's xne with what value of n? Applied to n. Xne takes a natural number and produces a proof that xn is not equal to c for that natural number. So I have that. And now where do I get this? hn. And now I know that f of xn minus L is less than epsilon, which is exactly what I'm trying to prove. Apply h delta. This argument here is when I saw this argument, I was like, oh, I got to do I got to do real analysis formally. This is one of the cleanest, it just works. Which epsilon should you use? That, the delta that comes out, stick that delta into the other thing, that you get the n, use that n. It's just like flows. Suha.
I still feel like the xn not equals c is like not because like isn't the statement you're trying to prove is like for any arbitrary sequence that approaches c? Like it's not like you have any freedom to choose that like the sequence of x is constant. So I feel like the condition's not necessary because all you're doing is like removing the triviality.
So look at HF.
Yeah.
HF says there's a delta so that for any x, if x is not equal to c, then I get this implication. And if x is equal to c, I can tell you nothing.
Yeah, wait, but isn't the hypothesis that I think I'm like confused where the for all is?
You mean here
No, like in the HF.
in the HF?
Like, is it like? I thought the hypothesis is that like it has to work for all sequences.
Yes. So we intro to sequence from the beginning.
Yeah, so you don't have any like freedom to choose what the sequence is.
Correct. I don't have any freedom to choose what the sequence is, but I insist because the theorem statement was, yeah, it's right here. This is the theorem statement. For all sequences, as long as that sequence is never equal to C, and the sequence goes to C, then the values of F go to L. So you're saying if I drop this condition,
Yeah.
but the definition of limit has that condition in it, and I won't be able to, I won't have it from
If it
anyone.
was uncon at when it would work.
Then it wouldn't work. Well, then it would work. Then it would work. If I had continuity, then I don't need this condition.
Okay, yeah.
Exactly right.
That's a
Yeah. Yeah. Question? All right. we're out of time. We'll finish the other direction next time. But we've entered function zone. We're gonna do some actual calculus.